Starting up again. So, today we're going to cover two topics, hopefully. So we're going to talk about epsilon regularity theorems, and we're going to talk about harmonic coordinates. So we'll kind of do one, then bounce to the other, then bounce back to the other. So I think I'll start with epsilon regularity theorems for a minute. So if I was going to give sort of a general spiel, the point is that this is a typical and sort of key ingredient for any good nonlinear PDE. Right? So, I mean, if you have a linear PDE, usually what do? You say you have a solution of something, maybe it's a harmonic function, and if the solution lives in L2 or something or whatever, then you say the solution actually has to live in a higher space, right? I mean, once you have some weak control, you have more control, right? I mean, if you know the L2 norm on some ball is 1, then on a ball of half that size, you know that the C infinity norm has to be bounded, right? I mean, if you have a harmonic function. For nonlinear equations, it's never quite so simple. You can't just sort of say you have a solution and it's bounded in some L2 or something and you get bounds on the smaller ball. I mean, there's two things you have to do. Is first off, you got to be careful about what you mean by bounded. So bounded in L2, bounded in H1, bounded in H20. It makes a big difference. And second thing you have to do is that oftentimes, especially, I mean, you want to make that first assumption as weak as possible. But when you make it sort of usually what that borderline weakness is, you can't just say it's bounded in this space. You usually have to say that its LP norm is small or something like this. And then once you get smallness of the solution in the correct space, then you actually get regularity on a smaller ball. And this is actually a key point, and it's very useful because smallness is something that's controllable, in fact. I mean, if it's just bounded, then that usually means that for most balls you can make it small, right? And that's usually the game you play. And that way you can't prove smoothness of the solution. It's a solution of a nonlinear PDE. It may not be smooth. But you can prove away from some subset it's smooth. And this is usually how it works. So in the same spirit, for Einstein manifolds or spaces with bounded Ricci curvature, we need epsilon regularity theorem. So these are things that say that if we have control in some weak sense of the word, then automatically this will imply control in some stronger sense of the word. And the game you play is that you want to make your weak sense of the word you want to make as weak as possible, because the weaker you make it, the more often you can force this to happen, and the more regularity you get out of your solution. So just as sort of a starting example, what I'm going to do is I'm going to state sort of the most classic epsilon regularity theorem in the context of Einstein manifolds. It is not in practice so useful, but it is, however, something that it was sort of, I mean, traditionally it was sort of the first thing to really be done. And at least in dimension 4, there were some actual applications. I'll discuss this maybe after I write down the theorem. We won't prove this. What will happen today is I'll state for you a series of epsilon regularity theorems that get better and better, and then I'll state one that's worse. And then we'll prove that. So just that way we can sort of, I mean, I'm going to, at some point either today or tomorrow, state some theorems that have been out in the literature for maybe a month. So these are quite, I mean, they're a little beyond where we are. But nonetheless, we can see what the starting point is and how to actually do it with some care for at least some example of an epsilon regularity. So where I'll start is the following. So theorem. And the theorem, I mean, this you can attribute to a handful of people, I think, under sort of slightly different contexts. So, I mean, Anderson, I think, in the way I'm about to say it, is probably the guy who did this, but also various versions of this appeared by Tian and others for some other purposes. And the theorem is the following. So let's let M and G P be usual complete pointed Riemannian manifold. And we're going to assume Einstein. So that means the Ricci curvature is identically some multiple of a metric here. With Einstein constant bounded. So for the sake of argument, I'll say bounded by n-1 because it's a nice normalization, but the bound itself is irrelevant. Just scale the space and you'll make it n-1. Then there exists an epsilon, which depends on just the dimension now. So not the Einstein manifold in question, not the lambda, as long as it's bounded, but just the dimension. Such that if the average on the ball of radius 2, let's say, around P, of the n over 2 norm of the curvature. So we look at the full curvature operator, we look at its absolute value, its norm, and we look at its ln over 2 norm, the average of it. So this is 1 over volume is what this sign here means. So we're integrating and dividing by volume. So its average is less than epsilon. Then, in fact, the sup of the curvature on the ball of radius 1 around this point. So a slightly smaller ball, right? Ball of radius 2 goes into ball of radius 1, is bounded by 1. So if we just know that the curvature in the n over 2 norm is small, then in fact we have a pointwise control over the curvature on a smaller ball. So this is sort of the most classic type of epsilon regularity theorem, where some sort of LP control gives rise to some sort of C0 control. Couple of remarks real quick, maybe. So for starters, I mean, the Einstein condition can actually be, we can replace Einstein with a bound on the covariant derivative of the Ricci instead. So it's not actually important that it equal a multiple of the metric. It's good enough just to have both the Ricci be bounded and the covariant derivative of the Ricci be bounded. Those two things need to be bounded, and you still get the same result. And in fact, I'll just say this right now because we haven't made the definition, but we will before the end of the day. You can even drop this condition, but you got to be a little careful here. The point is that if you drop this condition, this is somehow like a C2 condition on the metric here. You can't quite get a bound on the curvature if you drop this, but you can get a lower bound on the harmonic radius if you drop this. So this is really, I mean, we'll see how to rephrase this condition here in terms of a lower bound on the regularity scale, and it's basically like a C2 alpha condition, and then or a C2 condition, and there's like a C1 alpha condition called the harmonic radius that you can get if you drop this. They're basically equivalent, but you got to be a little technical about how you say things. Okay. I mean, roughly, you should think of it as saying, if the Ricci is balanced like the Laplacian of a function is bound, then you don't get a C2 bound out of that, right? You get a C1 alpha. So it's not reasonable to control a C2 thing. Okay. So we won't prove this at all. Let me just sort of tell you how the proof of this goes, because this is somehow the classic way of trying to prove an epsilon regularity theorem. Since we won't use this for anything, I'm not going to bother spending time on it. But the point is you prove it by Moser iteration. So the idea, I mean, sort of classic idea, right? So the idea is that you compute the Laplace operator of the Riemann curvature for an Einstein manifold. And you see it solves some nice equation. Heck if I remember what it is, but the Laplacian of the Riemann curvature is some function Q of the Riemann curvature. And you check what the powers involved here are, and it's just enough that this is the right power with the right epsilon that you can do Moser iteration, right? So you start to iterate up your LP norm on this. So if you have an ln over 2 norm, you can use this to force something that's in a little bit bigger than n over 2, but by using a Sobolev inequality, and you start going up. If you know Moser iteration, then you know what I'm talking about, and if you don't, you don't, but that's okay. The point being is that it's sort of it's a classic idea for sort of nonlinear equations. So I'm going to call this a weak epsilon regularity theorem. The reason being is that you want, I mean, so the point is that, weak control implies strong control, and that's good, but this is too much to ask. If you just hand me an Einstein manifold, there's no reason on earth you should be able to control this condition. It simply isn't reasonable to find balls of any radius where you have some hope of saying the n over 2 norm of the curvature is small. And because of this, that means that in practice, in general, you can't use this to prove a regularity theory, say, for Einstein manifolds. You can't just be handed an Einstein manifold and say, you have automatic regularity of this thing because you simply can't apply this to it. So we'll call this weak because this is a strong condition. So what we'll state after a little while, it'll take us a little bit to work up to it, but we'll state hopefully by the end of today what I would call a strong epsilon regularity theorem. The condition will look bizarre to you until at least one more lecture. But the point is that it'll end up being something that you really can control for an arbitrary Einstein manifold, so it makes it much more reasonable. Okay, but before we sort of move on to that, let's sort of change topics. So we've stated one epsilon regularity theorem real quick, and let's change topics a little bit so that we can sort of state future epsilon regularities in full generality. And this is a really just sort of useful tool anyway, right? I mean, in and of itself, ignoring the rest of this. So it's worth spending half a lecture on this. So that is the notion of harmonic coordinates. Okay, so we're always concerned with regularity of our geometries, right? We have a Riemannian manifold, and we're concerned with how regular that this geometry is. But of course, a metric on, like, say, a function on Rn, I mean, what you mean by regularity depends on the coordinate system you pick. You could pick a bad coordinate system where you don't have bounds on anything. That means just sort of nice bounds on anything. Or you could pick a good coordinate system where you have bounds on everything. And in the end, the real question is there some coordinate system for which this thing is bounded? And if there is there a way of somehow a priori knowing what the best coordinate system it is to pick? What's the best coordinate to find so that your metric in those coordinates has as much regularity as possible? And it turns out there is a canonical choice here. And they're called harmonic coordinates. In some sense, harmonic coordinates, you can even prove this make this a rigorous statement. I mean, your metric will have as much regularity or more than any other coordinate system. So you're going to play with an idea here. So let's just sort of jump into a definition real quick. So definition. So this is called the C1 harmonic coordinates. So let's let U, which will be, say, U1 through UN, be some mapping from the ball of radius R around P. This is inside some Riemannian manifold into Rn. With U of P being 0 and U being a diffeomorphism onto its image. So no statement's really been made yet. I'm basically just saying this is a coordinate chart. That's all that's been said. And it's a coordinate chart where, by assumption, it's mapping P to the origin. You can always shift a coordinate chart to force that. There's no assumption there. Then we call U a C1 harmonic coordinate chart. With, we'll say, U sub r is bounded above by 1 if the following hold. So the first condition, the Laplacian of each of these functions uk is 0. So the uk are harmonic. Hence the term harmonic coordinate system. So it's this diffeomorphism that's being generated by harmonic functions. So said otherwise, from a mapping from the ball of radius r into Rn is a harmonic mapping. The pullback metric Gij So this is on Rn now. It's a function on Rn. And it's given by, I mean, the same way any pullback metric is given by. It's as a function, this guy here. Satisfies Gij minus delta ij is less than, I don't know, I think I picked some random number here. Oh, that's good. Let's write all at once. That's better. So plus r times di djk is less than 10 to the minus 6. Just something small. Doesn't really matter what it is. Well, what is this saying, though? This is saying that, so we have our little ball in Euclidean space. That is our coordinate chart, right? Gij is the pullback metric on this. It's what our geometry looks like there. And we're saying it looks really close to Euclidean, right? In the C1 sense. Right? So it is pointwise close to delta ij, just the standard Euclidean. And the r here is a scaling factor. I'll explain that in a second. And its derivative is pointwise close to Euclidean metric. The r here, what that means is that this is a ball of radius r, right, supposed to represent. If I took this ball of radius r and rescaled it to a ball of radius 1, scale invariance would make this go away. So it just means that on the ball of radius 1 after we rescale, it's pointwise close to Euclidean space.
Is that it's grad UI, grad UJ, not XJ, right? Is that in the pullback?
Grad UI, grad UJ. U. What's that?
Is this the pullback under U inverse?
Yes, that's exactly the point, right? So this is the pullback under the diffeomorphism from U inverse. Right? So this is how you can write the pullback under any coordinate chart. I mean, that has nothing to do with harmonic. Right? So you can always write the pullback metric in terms of the inverse mapping, like just as the gradient. Okay, so that's it, right? So it just means that we have a coordinate chart where our pullback metric looks close to Euclidean. That isn't much of a statement. You could. I mean, this statement here, we could have always gone to a small enough ball and used exponential coordinates for. But the point is, then we're insisting, though, that the mappings be harmonic. This is the point. Okay. So what? I mean, I want to state a bunch of stuff about these coordinate charts, and I'll sort of outline for you how proofs go for these things. But since this is really not Ricci curvature, we'll be a little hand wavy about it some. I won't do it line by line, but we'll do it with some care because it's not so bad. Okay, so the first real question is, so what? So why would we expect this to somehow be a good coordinate chart for a metric? Why would we expect regularity from the metric from this coordinate chart? The key point is the fact that we're going to want to see that in these coordinates, our metric actually solves a nice PDE. So that if we solve some nice PDE, that this is exactly what you need to get regularity of higher order, right? So we're only going to assume C1 regularity here, but we kind of want to automatically get C infinity from this when we're actually being careful about it. So the following is a nice computation. It's basically just the Bachner formula being rewritten. So if we fix I and j and treat, so Gij, I'll say of x just to be clear, as a function now. I mean, it's supposed to be a 2 tensor, but now I'm saying we fix I and j and just treat it like a function on our coordinate chart. Then, let's make sure I get my signs right. The Laplacian of Gij. So this is the standard sort of metric Laplacian, but it's being applied to Gij, treating this like a function, right? If this were treating it like a tensor, it would be 0, right? So I'm treating this thing like a function. This is equal to minus 2 times the Ricci curvature in the ij direction, plus, well, some nonlinear nonsense, but it only depends on Gij and the first derivatives, Gij. So this is just some complicated nonlinear expression in G and the Gij's. What it is actually not so important for us. The point being it's of lower order, just first derivatives and less. It's arbitrary. No, it's arbitrary. I just wanted it small. Small should mean less than 1 so that this thing is positive definite, right? And that's really, it has to be, I mean, it's got to be that this thing is at least an honest metric tensor, right? So, that's really it, right? Less than 1, so the eigenvalues of this thing are strictly between, bigger than 0 and, less than 2 or something, right? It's pretty arbitrary except for that. It can't be 10, right? It's got to be less than 1, but past that it doesn't really matter. Yeah.
Handwriting question. What's the after 2? Is that an I?
After 2,
So in the formula with Q, parenthesis, G, I,
oh,
J,
partial.
partial. Okay,
Partial. My 2's and my partials are, let's change my 2.
So partial. Okay.
There we go. Let's change my 2's. All right, so that this means the first derivative. Okay. So what can we do with this? What's the basic corollary of this? So really, what do we do? I mean, I'm not going to do it, but it's the Bautner formula, right? You're computing the Laplacian of this thing here, right? That this is a computation we've done 10 times, right? So we get a Laplacian that comes inside, a Laplacian that comes inside. You commute derivatives to get your Ricci curvature term. And the rest ends up being like a Hessian of this thing times a Hessian of this thing, which you can just rewrite like this. So it's the Bautner formula in disguise. But what's a nice corollary of this? And this maybe will actually prove a little bit. So if U from the ball of radius r around P to Rn is a C1 harmonic coordinate chart, with C1 bounds, then the following hold. If, let's say, the Ricci curvature is bounded above by, it actually doesn't matter what I bound, A is fine, but let's just say A. Why not? Let's just do A so that we can be clear about this. Is bounded above by something. I mean, it's smooth manifold. It's always bounded above by something, but we're being quantitative about it. It's bounded above by some A. Then for every alpha less than 1 and every q less than infinity, we have that if we look at the partial derivative of Gij, our metric in the coordinates, and we look at its C0 alpha norm. So we're going up a derivative, or up alpha derivative here. Then this is actually bounded above by some C of NA. And likewise, if we look at the 2 plus Q times the average over the ball of radius, say r over 2, I guess. Oh, sorry. Now let's make this a 2r here so I can do all this on the ball of radius r. So usual regularity, right? We're going to have something on the ball of radius 2, and then I want to say something about the ball of radius half that radius. I can make these balls of radius half the radius, but I'll normalize like this instead. And if we have this Ricci bound, then if we look at the second derivatives, KL, of the metric, then, well, they aren't whole or continuous, but they are in some LP or some LQ for every q less than infinity. This depends on alpha. So the point is we just started assuming these things were actually having C1 bounds, but automatically once we know the Ricci's bound, that then in fact they're in C1 alpha for all alpha less than 1, and W2Q for all q less than infinity is what we're saying. So this is with no change of the coordinate, right? Same coordinate system. It just turned out it had more regularity than we thought it did. Let me just write down 2 more that'll be useful. Likewise, if we actually have a bound on not just the Ricci, but the covariant derivative of the Ricci, then what we see is that for every alpha less than 1, we have that r to the 2 plus alpha of this C0 alpha norm of the second derivative is actually bounded. So in other words, our metric was now automatically in C2 alpha for every alpha less than 1. And finally, one last thing, just to throw it in there. If the Ricci is actually a Einstein, so it's a multiple of the metric, then for every k, we have automatic bounds of the kth derivatives of our metric. So that is, these coordinates are going to automatically capture as much regularity as actually true. We only assume C1 control, but it will capture all regularity above that automatically. So let's at least prove one, and the others are exactly the same. So, proof of one. So where does this come from? In fact, it comes from our computation of the Laplacian of the metric. Right? So we computed the Laplacian of Gij in our coordinate system is minus 2 times the Ricci Ij plus q of our g and partial g. So if the norm of our Ricci is bounded by A, then by assumption, our metric here looks very close to delta ij. So that actually implies that in our coordinates, when we're looking at these components here, that this here is just the absolute value of a number. I mean, this is less than or equal to, well, roughly a also, but let's just say a plus, what is it, some 10 to the minus 6, roughly. I mean this roughly. It's not exactly that, but I'm basically saying it's a plus whatever the error is from this being the metric, because this here is GAB, GCD, RAC, RBD, right? So I mean this is the definition of this guy here. Let me square it so I can do that. So if I replace these by delta ij's, then we get our bounds for the eigenvalues, since we get our bounds for our components. So in components, we have some bound for whatever this is. And we also have a bound for pointwise bound for g and a pointwise bound for the partial derivative of g. So we also have that q. And this was without any assumption, really. Has some bound that's, maybe depends on dimension, because it depends on how many elements we have in here. But it's bounded by something, just because g and the partial derivative g is, and there's some linear expression, a quadratic expression in them. But what does this mean? This automatically means that the Laplacian of Gij in our components is bounded above by what? This plus this. So something that depends on n and a. But this is just elliptic regularity now, right? We know this thing is bounded on the ball of radius 2r. Its Laplacian is bounded. That automatically means that we have C1 alpha bounds in the ball of half that radius. So this plus, actually, even just C0 bounds. Implies C1 alpha bounds. So the point here of harmonic coordinates is that we're forcing a coordinate system where the components of the metric tensor solve an equation. So we can use elliptic regularity on it. Okay. So, just to say in words, I mean, how would you do 2 now? The point is that once 1 is done, and you have C1 alpha bounds on your metric, then in fact Q is automatically itself in C0 alpha at least, right? Because we already have C1 alpha bounds. The same game will show the Ricci tensor actually has C0 alpha, I mean C1 bounds, so in particular C0 alpha bounds. But now elliptic regularity says that means that since the Laplacian of this thing is equal to something in C0 alpha, the metric itself has C2 alpha bounds. Okay? And you just keep iterating your way up. So it's called bootstrapping, by the way. So anyway, roughly speaking, that's how it goes. Okay, fine. So everything involving harmonic radius here will be a little rough because I'm going to go through this sort of as a reminder, a review. The book by Peterson does this all very well, by the way, very carefully. Okay, so what's next? So the next thing we really want to do with all this, so we've picked coordinate charts that we like. So we like harmonic coordinates. So that somehow regularity now of the metric, really you should identify it with what's the largest ball around a point for which you can find harmonic coordinates. Because the only thing controlling the regularity of everything here, right, well, was this R. Right? Somehow we automatically say you're an Einstein manifold just for the sake of argument, right? Then the point is the only thing stopping you from looking very regular at a point is how big this ball can be for which you have harmonic coordinates. So regularity, it's not a whole bunch of numbers. It's not about C1 bounds of the metric or anything like that. It's more like a lower bound on the size of the ball you can find harmonic coordinates on. So this is actually a sort of an important notion for all nonlinear PDEs. You call these things regularity scales. So what we're going to do is define some regularity scales now. We'll actually define 2 types of them. Yeah, so, I mean, clear, I mean, no. Provable, yes. So roughly speaking, it's not hard either, but I really didn't want to, I mean, that would definitely be half a lecture. But what do? So exponential coordinates certainly exist, right? So what you do is you basically take exponential coordinates, look at a very small ball, and use an inverse function theorem to prove that you can perturb those coordinates into harmonic coordinates. That's roughly what happens. I was going to get to that after the definition, actually, but yes, that's exactly how it goes. So let's let some manifold be smooth. With x inside M. Then we define the harmonic radius. to be the largest radius, less than or equal to 1, say, just for the sake of argument. Or actually, because of what's going to come, let's say less than or equal to 2. Such that there exists a C1 harmonic coordinate chart, U, and the ball of radius R, around P, X, sorry, into Rn with C1 bounds. So we're just asking, how big of a radius can we find such a ball? Somehow, like if we're on an Einstein manifold, right, the point is that now we know we can control just about everything from this. Actually, I'll make that more explicit in a second. Similarly, we define the regularity scale. As almost the same thing, but it's equal to the max of all, let's say, 0 to r less than or equal to 2, such that if we look at the ball of radius r around P, and we look at the curvature on that ball of radius r, x, then it's bounded above by r to the minus 2. Okay, let's maybe have a couple remarks about this before we move on, because it's slightly strange looking at first glance. So let's note a couple things. So the harmonic radius is always somehow let's make sure I say this correctly. Is always somehow a weaker thing than the curvature scale. So what's that mean? So that is to say that this is more or less a rephrasement of the question he asked a second ago. There exists some dimensional constant such that we always have that the harmonic radius is bounded from below by the curvature scale. This is not so entirely obvious, but the point is what? So what is this controlling here? So this is saying that we can find a ball of radius r, right, where the curvature is bounded on this whole, on the whole ball, the curvature is bounded by r to the minus 2. Why r to the minus 2? Because it's scale invariant. That is the game we always play, right? So that means that if I took this ball of radius r and I rescaled it to a ball of radius 1, then the curvature would be bounded by 1 on the ball of radius 1. Once you have that, the point is that you can get automatic control on your exponential coordinates. And in particular, playing the game we were just discussing about inverse function theorems, you can force the harmonic radius to exist on some ball of definite size. So that is to say, once you have a curvature bound, you can certainly find harmonic coordinates of a definite size. Let's say the scale invariance a little bit more carefully. So both these things are defined in the following way. So if we were to rescale the ball of radius, the regularity scale at the point, to the ball of radius 1. So I'm taking my Riemannian manifold and multiplying it by this guy minus 2. So it just takes that ball of radius r to a ball of radius 1. Then after rescaling, the soup on the ball of radius 1 around x of the curvature is bounded above by 1. And the last point I really want to point out about this is that, in fact, well, we have another converse. So the last corollary implies that if M is Einstein, then we have the opposite inequality. So that is the harmonic radius bounds from below the regularity scale. So how do we know that? The point is, this here is saying that, well, on the ball of radius r, well, we can find this harmonic coordinate chart. Then our corollary said that on a ball of half that radius, we can get as many bounds on the derivative as we want. In particular, we can get C2 bounds on the derivative. The curvature is just it's just a function of two derivatives of the curvature. Once you have bounds on two derivatives of the curvature and on the metric and on its inverse, well, you have bounds on the curvature, in fact, because it's just a function of two derivatives of the metric. So in particular, the curvature is bounded by something, which means the regularity scale, you drop the corresponding number of radiuses down, and is bounded from below by something too. So in other words, for Einstein manifolds, regularity scale and harmonic radius are equivalent. For bounded Ricci, though, they are not. It was sort of the point, right? So if we were to, harmonic radius is really, for bounded Ricci, harmonic radius is like a C1 alpha guy, right? It's C1 alpha control over our metric, whereas curvature is a C2 control over our metric. And if we only have a bound on the Ricci, which is like a bound on the Laplacian of something, it's not reasonable to ask for C2, but it's perfectly reasonable to ask for C1 alpha. Okay. So one more point about harmonic radius and the regularity scale, and we get to move on from it. So this is actually, this is a really nice theorem that I'm going to write down. We're going to use it at some point, but we're not going to prove it. It's really about curvature bounds, not Ricci curvature. So the moral for it goes back to the late 60s, probably the thesis of Cheeger, where these sorts of ideas first appeared. So he didn't say it quite like this, but more or less the proof of this follows the same way. The theorem. So let's consider a sequence of Riemannian manifolds. Which are complete, as always, and such that for every x inside them, the regularity scale, or the harmonic radius, doesn't matter, let's say harmonic radius, is bounded from below by something. So this something here, it's independent of the point, it's independent of the sequence. So it's saying that we got this collection of Riemannian manifolds, and for every one of them, and for every point, there is a ball of definite size where we have geometric control. That's what this is really saying. So what do we usually do with sequences of Riemannian manifolds? What we've been doing with them is we've been, at least passing to subsequences and making them converge in a Gromov-Hausdorff sense to something. So we want to do the same thing here. We want to say, first off, that there is a subsequence that will converge in the Gromov-Hausdorff sense. But what it's converging to should be well behaved. It should not be an arbitrary metric space now. In fact, we're going to see it's an actual manifold. And then there exists some other Riemannian manifold, MGP. such that, well, after passing to a subsequence, so the first point is that a sequence of Riemannian manifolds have to converge in the Gromov-Hausdorff sense to this Riemannian manifold. Note, by the way, there's already, I mean, these are the same dimension, right? I mean, much better we can pick Gromov-Hausdorff maps phi from, say, the ball of radius r in this space. So remember, I should really say that for every r. So remember, point to Gromov-Hausdorff convergence means Gromov-Hausdorff convergence in all balls. And our Gromov-Hausdorff maps between the ball of radius r around pi and the ball of radius r around p. Well, it's a diffeomorphism. I want to stay under this for the theorem, so let's get rid of my remarks. To be diffeos. In fact, C1 alpha diffeomorphisms. Such that, so not only these diffeomorphisms, but the point is that what I mean by C1 alpha here is that if I take the Riemannian metric, Gi, on Mi, I pull it back to a Riemannian metric now on M, then these will converge in C1 alpha to the limit metric G. So we don't just have this sort of terribly weak notion of isometry where we have these sort of epsilon nets that are converging out. We have an honest C1 alpha convergence of our spaces. And then the other conditions are much the same. So if the Ricci is actually bounded above, so if the Ricci's of all these guys are actually bounded above by something, then in fact the pullback metrics converge in C2 alpha. The G. And if all these guys are Einstein manifolds. Then for every k, the pullback metrics converge in CK. The G. Note a really interesting application of this. If the diameters of these Mi are all uniformly bounded by some d, then what this is saying is that for large enough in the sequence, they're actually all diffeomorphic to each other. And in particular, they're diffeomorphic to M, the limit space, and so diffeomorphic to each other. This sort of, yeah.
So I was wondering, instead of, maybe it's a bit tangential, but instead of using this harmonic radius, if you use injectivity radius and specify it, so I guess what I'm asking is, if you are constructing harmonic
Yes.
perturbing the exponential coordinates.
Yes.
A lower bound on the injectivity radius, can it force a lower bound on the
On the harmonic radius. Right, yeah. So as long as you have a bounds on the Ricci curvature, I mean, the answer is yes. Right, so under bounds on the Ricci curvature, a lower injectivity implies lower harmonic. In general, the answer is no. So the point is that you could try to play the same game with injectivity radius, but you'll lose derivatives and all the convergence going on here is the point. I mean, you actually gain less than you could have gained by looking at better coordinates.
In 4G, you need a uniform band on the size of the band.
Yes. I almost feel like that's implicit in this, but let's go ahead and just say it. So what she's saying is, I'm actually not convinced we have to have it because of the lower bound there, but let's go ahead and assume it. Okay, so the first real application of this way back when, right? So in particular, right, if I mean, instead of having a harmonic radius lower bound, if you have a lower bound on the curvature scale, the regularity scale, you can make all the same statements because that controls the harmonic radius. This lets you prove, for instance, that the collection of Riemannian manifolds with diameter bounded by D, sectional curvature bounded by A, and volume bounded below by V, say, have finite diffeomorphism type. I mean, that this was the first real theorem of the spirit that says that if you have, like, so from a geometric point of view, those three things are everything in geometry. Right? I mean, you really can't control more in some sense. So once you control those three things, though, you control the topology. I mean, the topology can't change infinitely often. And you do it by proving it by contradiction. You assume it's not true. You pick an infinite sequence of guys that are all supposed to not be diffeomorphic, but I mean, this basic construction here says they all become diffeomorphic past some point, namely this note right here that constructs the diffeomorphism with the image. We won't do that. I'm just throwing it out there. Okay, great. So I think what I'm going to do is give one more pounding definition, because that way when we come back tomorrow, we can just start sort of stating interesting things and proving interesting things without having to worry about definitions anymore. I've been sort of keep meaning to define cone spaces carefully for you, and I always have 5 minutes at the end, and that's just enough time to state what I want to state and not actually do something except draw a picture for a cone space. So I'm going to give you a definition of a cone space real quick so that when we come back, because the epsilon regularity theorems we're going to care most about will involve cone spaces. So I do want at least a careful definition of a cone space, at least when the cone section's a smooth space. And then we'll come back to epsilon regularity theorems tomorrow, right away, because we're done with harmonic radius at this stage. So, definition. So let's let Y be a compact manifold. Then we're going to find the cone over Y. Let's go ahead and let's put this on the next line. So we mean two things by this. So first, we mean the topological cone. So that means we look at Y cross 0 infinity. And then we mod out by Y cross 0. This isn't anything complicated. That just means this here is our Y. And, you know, we take it, we product it by an interval, 0 to infinity, but then we take that 0 and we crunch it up to a point. So this is the topological cone. Same definition as the cone space in topology. But now, as geometers, we want to put a geometry on this. So we're going to put a metric. G, which is going to be dr squared plus y squared g sub y. So we take the standard metric on the cross section, the y part there. We look at the, so if we dropped this r squared here, right, what would it be? It would be the standard product, right? It would just be r cross y is all it would be. But the r squared in front of it is going to squish that down to a point at the origin. So it gives us geometrically this picture here. So this will always be a smooth manifold away from the origin. And there's one case now where it's still a smooth manifold itself. So there's one example where if we look at the cone space over some smooth compact thing, we get something smooth back from it. And that example is the standard n-1 sphere. This is a nice exercise. So if we look at the n-1 sphere, standard n-1 sphere, we look at the cone over that, what do we get? We just get Rn. So this is basically polar coordinates, right? So we're just reviewing Rn in terms of its cross-section, which is the sphere. If we make that sphere smaller, then we get this picture here, right? But for the standard sphere, we get Rn back to it. That'll actually be an extremely important aspect in the proof of an epsilon regularity theorem tomorrow. So I really want to point this out, that the only cone space that actually is a smooth manifold is Rn. Okay, so tomorrow, so let's actually just do plan for the next couple of days. Tomorrow, I mean, the next few days, so at this point, I think we've done most of the technical stuff, actually. I mean, there's still some technical stuff to come, but I mean, at this point, we're going to start getting more advanced very quickly, which tends to mean that we do more intuition and less computations very quickly because we only have so much time. Tomorrow, we'll focus on epsilon regularity theorems. So I'll state for you sort of, what the most recent epsilon regularity theorems are, and then I'll state for you a more basic one, which we will actually prove in some detail, and it's a fantastic proof. And then after that, we'll start talking about stratifications and quantitative stratifications of limit spaces. The reason for this is because what we're going to want to work our way up to, certainly by Thursday, is an actual regularity theory for Einstein manifolds. And for that, we're going to have to be able to see how to actually apply these epsilon regularity theorems, and for that, we'll need the stratification theory and the quantitative stratification theory. Okay, we're done. Go away.